One of the important things we want to be able to do at this level is understand how bit operations affect the time complexity of an algorithm. So we're going to look at a couple of examples here. These are the types of questions you might see where we try to actually compute either how long it would take an algorithm to solve a problem of a certain size or how big a problem you could solve with a given amount of time. We're going to deal with that latter part first. We're going to suppose that a computer can perform 10 to the 12th bit operations per second. So that means in 1 second, you could perform 10 to the 12th bit operations. We want to find the largest problem size that can be solved in 1 second if an algorithm requires a certain number of bit operations. Okay? So in 1 second, we can perform 10 to the 12th bit operations. Right? That's the thing we're starting with here, 10 to the 12th bit operations per second. The first algorithm requires n to the 4th bit operations. Now in 1 second, you should be able to perform 10 to the 12th bit operations. So really the question here is when does n to the 4th equal 10 to the 12th? Right? So the goal here is to figure out what would make n to the 4th equal 10 to the 12th. Well, if we want to solve for n, we could basically just raise each side to the 1/4 power, raise each side to the 1/4 power, and what you'll get on the left is n. And if you raise 10 to the 12th raised to the 1/4, you end up multiplying the two exponents together, and you'll get 10 cubed, or 1,000. So if you have a problem of size 1,000, then an algorithm that is n to the 4th, that requires n to the 4th bit operations, would take that 1,000 10 cubed, raise it to the 4th power. That would give you the 10 to the 12th bit operations that this computer can do in 1 second. So while n to the 4th is a large number, you could still solve a problem of size 1,000 in a second. Okay? Now, what we're going to look at over here is going to be a slightly different story. With 2 to the n bit operations per second, the question really is, when would 2 to the n equal 10 to the 12th? Okay? Now, in order to solve an equation like this, we'd have to either rely on a little bit of algebra that we may or may not remember, or we can get a calculator out and do some guessing and checking. While in theory we should remember the algebra, I'll do the guessing and checking method first, and then I'll show you how to do this algebraically. But remember, if you're solving an equation that has the variable stuck in the exponent, you're going to need logarithms to do that. Okay, so if we did a little bit of button pushing on our calculator, we would find that 2 to the 39th is roughly 5.5 times 10 to the 11th. And if we did 2 to the 40th, we would find that that's roughly 1.1 times 10 to the 12th. So we're at 2 to the 40th, we're actually over 1 times 10 to the 12th. We're pretty close. But we did slightly go over the 10 to the 12th bit operations per second. So we can't actually take the 39, the 40, we would have to take 39. So in a case like this, we can only solve a problem of size 39 in a second if we were dealing with 2 to the n bit operations. Okay? So with a little bit of button pushing and a nice enough calculator that has this kind of significant digit display, you should be able to get pretty close to the answer with a few button pushes. That might be the easiest way to go. But since we are capable of doing this algebraically, let's think about how we would solve the equation 2 to the n equals 10 to the 12th algebraically. Well, since we have exponentials with different bases, what we're going to do is take the log on both sides. Log of 2 to the n equals log of 10 to the 12th. And we'll use log base 10 here. Now, a lot of times, and you'll see in this textbook, when we're dealing with programming, which is done on binary systems, the log is often assumed to be log base 2. But I'm referring to log base 10 here. Exponent rules allow us to take the n out. So you have n times log 2. And if you take log base 10 of 10 to the 12th, you just get 12. So if you wanted to solve for this algebraically, you could say n equals 12 over log base 2, which is going to give us, I believe, 39 0.86, something like that, which is the same 39, almost 40 that we saw up here. So if you were asked to figure out how big a problem you could solve and you had an exponential function here, you could either plug some numbers in and just try to get the closest one without going over the number of bit operations you're allowed, or you could try to solve algebraically and pull your calculator out to do the logarithm. Okay? Now the reverse question to this is, how much time would it take to solve a problem of a certain size? So the examples here, you knew how much time you had. You had 1 second, which equated in this case to 10 to the 12th bit operations, and you wanted to know how big a problem you could solve. This set of questions here, same computer that can perform 10 to the 12th bit operations per second. Now we want to know how long it would take for an algorithm that requires n cubed plus log n operations with a problem size of n equals 1,000, and then again with n equals 10 to the 8th. Now, this log n, as we'll see in our book, really means log base 2 of n. Okay? So our function that we're computing is n cubed plus log n. This is the number of bit operations. So if we take 1,000 cubed and add that to log base 2 of 1,000, right, that's going to give us a number of bit operations. So we can get our calculator out and compute a value for that. Okay. Now if we cube 1,000 here, we're going to really get 10 to the third, which is 10 to the 9th. And if you take log base 2 of 1,000 on your calculator, you're going to get roughly 10. Okay. Now, in the grand scheme of things, 10 to the 9th plus 10 is really basically 10 to the 9th. But if we wanted to be complete, we could say 10 to the 9th here. That's 10 to the 9th, 3, 6, 9, and then add 10. This is the number of bit operations this algorithm would require. So let's just, for simplicity's sake, just refer to this as 10 to the 9th. Okay. If you have 10 to the 9th bit operations, and you can do 10 to the 12th bit operations in 1 second, okay, what I did here was set up a ratio so that I had the unit cancellation, bit operations cancel, leaving me seconds on the top. That's going to give me 1 over 10 to the 3rd seconds, which is 1/1000th of a second, okay, a millisecond. So even a problem the size of 1,000, right, on a fast computer like this could be solved in a fraction of a second. Okay. Basically, the strategy is the function up here tells you how many bit operations it's going to take. You know in 1 second how many bit operations you could do. You have bit operations per second up here. We just turn that the right way so you get the unit cancellation that you need. So the 10 to the 9th over 10 to the 12th gives us 1 over 10 to the 3rd. Sometimes they'll give this to you to say that 1 bit operation takes 10 to the negative 12th seconds, in which case you would just put the 10 to the negative 12th up here and then 1 bit operation down here. You just set the ratio up so you get the unit cancellation you need. Okay. Now for this next example over here, the function again is going to be n cubed plus log n. This is going to be 10 to the 8th cubed plus log base 2 of 10 to the 8th. Okay. Now this is going to be 10 to the 24th. Okay. We'll put an approximate here because this log base 2 of 10 to the 8th is roughly 26.6. Now again, in the grand scheme of things, this 10 to the 24th, adding 26 to it is going to be relatively insignificant. So we're going to do 10 to the 24th bit operations times 1 second over 10 to the 12th bit operations, again to get the unit cancellation that we want. Just make sure this is clear. And that's going to give us 10 to the 24th over 10 to the 12th, which will give us 10 to the 12th seconds. Okay? Now, what does 10 to the 12th seconds really mean? Okay, well, we could, just for interest, this would be fine for an answer, think about how much real time this would be. Okay, so if we started with 10 to the 12th seconds, we know that it takes 60 seconds to make 1 minute. We know it takes 60 minutes to make 1 hour. Okay, we know that it takes 24 hours to make 1 day, and we know, give myself a little more room here, that it takes 365 days to make 1 year. We'll disregard the extra quarter of a year here. And we'll get out a calculator and perform this calculation. We'll take this 10 to the 12th, we'll divide it by 60, you get divided by 60, divided by 24, divided by 365. And if you get your calculator out, that will turn out to be roughly 31,710 years. Okay? So think about that for a minute. An algorithm, n cubed plus log n, on a problem of size 10 to the 8th, it's going to take a long time to finish. That's simply just too long for a program to take to finish. Okay?